And the fourth is osmosis and osmotic pressure. So when you add something to water, let's say we add salt to water, you will lower the vapor pressure. Water that can't escape as well because salt is blocking it. And also it can't freeze as well because salt is blocking it. It has to exclude the salt before it forms a crystalline solid structure. And so the net results are the freezing point goes down and the boiling point goes up. And so if you add a bunch of salt to water, the freezing point goes below 0 and the boiling point goes above 100 degrees. And this is doubled down on in your car because you can call the ethylene glycol as both coolant and antifreeze because it's just based off the colligative properties. And therefore, it's antifreeze because your coolant won't freeze when normal water would freeze. And it's also coolant because it won't evaporate when normal water would evaporate. Because due to the colligative properties of the ethylene glycol, the freezing point has been depressed way lower and the boiling point has been elevated way higher, which is why antifreeze and coolant are the same thing. Because the colligative properties raise boiling point and they depress freezing point. When we deal with that, we need to work with molality, which is like molarity, except instead of liter solvent or liter solution, it's kilogram solvent. And it's signified by a small m. So what is the molality of a solution prepared by dissolving 0.1 moles of starch in 0.5 kilograms of water? 0.2 molal, and this is signified by an italic small m for molality, which is different than molarity. What is the molality of a solution prepared by dissolving 2.7 grams of methanol in 25 grams of water? Well, first we convert grams of methanol into moles like we learned in chapter 7. And then we have to convert grams of water into kilograms for the molality equation because it's per kilogram of solvent. And we get 3.37 molal. To calculate the colligative properties, the change in freezing point or boiling point depression will be the molality times a constant. There are different constants. Freezing points use Kf, boiling points use Kb. Notice they're different. For water, Kf is 1.86, whereas Kb is 0.512. The freezing point constant is always different than the boiling point constant. So when you're using freezing points, you subtract the delta T from your freezing point because it's getting lower, and you use Kf. When you're doing boiling points, you add the delta T to your boiling point because boiling points are going up, and you use Kb. So what is the boiling point of a solution prepared by dissolving 0.1 mole of sugar in 0.5 kilograms of water? Well, again, we did this already. 0.1 moles of sugar in 0.5 kilograms of water is 0.2 molal. And now we times it by the Kb of water because we're looking at the boiling point elevation. And we get a delta T of 0.1. And because it's boiling point elevation, we add that on top of the normal boiling point to get 100.1 degrees Celsius. So by adding 0.1 moles of sugar to water, we've raised the boiling point of water from 100 degrees to 100.1 degrees. What is the boiling point of an aqueous solution that is 4 molal? Well, it'll be 4 times 0.512. We get a delta T of 2.05, and they're asking about boiling point, so you add that to the boiling point, because boiling points go up. If we're dealing with freezing points, you'd subtract that, because freezing points go down. And again, with freezing points, you'd use Kf, not Kb. So now let's do freezing point depression. What is the freezing point of a solution prepared by dissolving 0.1 mole of sugar in 0.5 kilograms of water? Again, it's 0.2 molal, but we times that by Kf, 1.86, and we get a delta T of 0.37 degrees Celsius. But since this is freezing point, we subtract that from 0, because we depress the freezing point to get negative 0.37 degrees Celsius. And this is why we salt roads in the winter, because as the salt gets mixed into the ice, it lowers the freezing point to the point where it won't freeze at the temperature outside and it becomes liquid. As the cars drive over the ice, you apply pressure to water and you melt it actually with the pressure. Because ice has such an open crystalline structure that when you apply pressure to it, it actually melts instantaneously. And that gets the salt dissolved into the ice, and then you lower the freezing point and you'll slowly melt all the ice, which is why salt is effective. Melting ice with pressure is why ice skating works. All of your body weight is on two little blades as you go over the ice. It's enough pressure that as you're skating, you have a temporary film of water under your skates, which give you that fluidity. Now, there's a temperature at which that stops working. I mean, it's really cold. I think it's like -40 or -60 Celsius. But it can get cold enough where you stop making that film of water because it's too cold, and then ice skating stops working. What is the freezing point of 100 grams of ethylene glycol dissolved in 200 grams of water? Well, we have to convert grams of ethylene glycol into moles. We use our trusty periodic table. We add 2 carbons, 6 hydrogens, and 2 oxygens to get 62.07 grams. That's 1.61 moles over 0.2 kilograms, because 200 grams is 0.2 kilograms. And we end up with 8.05 molal times the Kf of water, which is 1.86, gives us a depression point of 15, -15. So if I double this, if I have 200 grams of ethylene glycol and dissolved into 200 grams of water, you depress the freezing point to -30 Celsius. And that's pretty much what antifreeze is in your car. You have a mixture of ethylene glycol and water, so that even at -20 or so, it still functions. If you're going to be in ridiculously cold climates, you have special car fluids and special oils that deal with extreme cold. But if you're in Iowa, it's not going to get to -30, because that does not include wind chill. That's just temperature.
What do they add to diesel fuel in the winter? You know how they like
The winter blend?
Yeah.
Diesel is thicker than fuel. In the winter, you need to have a thinner version of it, or it'll coagulate. Just like in the winter, you can use thinner oils. In the summer, you can use thicker oils, but those would freeze in the winter. Same type of thing. You need a thinner mixture so it doesn't freeze up in the winter. And then in extreme situations, like there's research stations in Antarctica, you can't shut a truck off. They run 24/7. Because if you turn it off, you won't turn it back on. Things will freeze up. And so they just run vehicles 24 hours a day, 7 days a week. You refuel them while they're on, and you have to because it's just so cold. Things will freeze up if you ever shut things off. But yeah, you need thinner fluids in the winter, both oil and the diesel fuel. Gasoline is so thin anyways, it doesn't matter. And so you can keep using gasoline, but they actually do sell different blends in the summer and the winter. It's just that they don't really market it that way. But the stations do get different formulas in the summer and the winter. Osmosis. This is the diffusion of water through a semi-permeable membrane, which only allows water to go through. We talked about that a little bit last chapter. Osmosis is the diffusion of water, but from the perspective of water. How is water moving? Water, like anything else, wants to move from high concentration to low concentration. And so the more salty or the more sugary something is, the salts and sugars are taking up space that could be water. So that means the more salty something is, the less watery it is, because salt is taking up space that could be water. And therefore water wants to enter it. The pressure you must apply to a solution to stop pure water from entering it through a semi-permeable membrane is the osmotic pressure of a solution. So the more salty or the more sugary something is, the higher the osmotic pressure. Because the more water wants to enter it, so the more pressure you would have to apply to stop water from entering it. And so in this case, water keeps entering this sugar solution until the weight pushing down on it is enough to stop it from entering, and that is your osmotic pressure. And relative to body concentrations, these can be isotonic, hypertonic, or hypotonic. Isotonic has the exact same concentration as the body, same osmotic pressure. If something is going to be given IV, it must be isotonic. You don't want any osmotic differentials in venous tissues. Hypertonic is something way more concentrated in the body. And so if you added something hypertonic, it's going to start sucking water out of your adjacent cells to try and neutralize it, like salt water. So if you have to inject something hypertonic, it's not done often, but you can go through an artery because it'll get diluted very rapidly. So on the rare occasion that you inject into an artery, it's just because it'll rapidly dilute because you have so much pressure on the arterial side of your circulatory system. Whereas on your venous side, there's not much pressure at all, and so things can pool up, which is why varicose veins can occur. Blood itself pools up and causes those veins to occur. Hypotonic has much lower concentrations of salts than body fluids, like distilled water. So if you drop human red blood cells into distilled water, the water keeps entering them until they explode. Animal cells don't do well with hypotonic solutions because they don't have a cell wall, and so they will explode eventually. Whereas plants can do fine with it because a plant has a strong cell wall, and so actually a lot of plants use this pressure to hold themselves upright. Herbaceous plants are plants that don't make wood, and they actually use water pressure to hold themselves up. They just pump themselves full of ions so that the water comes in through osmotic pressure and overinflates them. But the cell wall is cellulose, it's wood, it's strong, and so it can hold that pressure, and the plant uses that pressure to maintain its structural integrity. And if it loses that water pressure, it wilts and falls over. All right, that is the end of chapter 14.